Number 15 here in 4.7, I think, is a really interesting question, and it's a good test for how well you guys understand a couple of concepts. Number one is the basic thing that we're trying to do here within 4.7, which is to maximize or minimize something. And here, we're trying to maximize the area of an isosceles triangle that's given to us by this formula right here. But the other thing to realize here, guys, this is also a test for how closely you can read this right here. We're supposed to find the angle, theta, this angle right over here, that can maximize this. So I want you guys to think of this being a hinge right here, and this being this angle either opening or closing, wider or narrower, and we're trying to come up with the maximum possible area. So one of the things we could do, let me draw you a couple variations on this. If we closed this angle theta, we would end up with a very tall and skinny isosceles triangle like this. And that one isn't going to have a very big area because its base is relatively small. On the other hand, if we open theta up almost as wide as we could end up with a funny little triangle that looks maybe something like this. That has a very wide theta right here. But in that case, it's not going to have a very big area because its height is relatively short there. But the important thing here is, and I think this is what bothers most people about this problem, the length of the legs of your isosceles triangle here is L, and L is not a variable in this problem. They're asking us to find the angle, theta. That's what's changing here to maximize the area of this triangle. So in either case that I drew right here, all of these legs are all going to be the same length. And whether that length is 5 inches long or 7 feet long or 11 meters long, it doesn't really matter. The problem is still the same. We want to know what value of theta is going to maximize the area of this triangle. So in that regard, guys, step one, actually really in step two, there really is no step one here. Step two is already done for you. We're trying to maximize the area of the triangle. Here's the area equation. Area is equal to 1/2 times L squared times the sine of theta. That is a variation on the formula for area of a triangle that you guys may have learned at some point along the way, and if not, don't worry about it. They gave you the formula. Well, we have an equation right here that tells you A as a function of theta, and L is not a variable. L is a random, arbitrary constant, but it's not going to change through the course of this problem. So that is everything you would have normally had to accomplish in step one and step two. Now we can go right into step three. Let's find A prime here, everybody, or better yet, the derivative of A taken with respect to theta. That's going to equal, all right, well, all of this is a numerically constant coefficient. So we just start this thing with a 1/2 L squared and then multiply that by the derivative of sine of an angle, which is cosine of the same angle. That's it, guys. That's your derivative. So we're going to set that equal to 0 and solve. The first thing I would probably do here is divide both sides by a 1/2 L squared, which I know I can do because L can't be 0. So a 1/2 L squared, and that cancels with that. Oh, and now this isn't that bad. I get cosine of theta is equal to 0 divided by anything non-zero is 0. And now theta then becomes the inverse cosine or the arc cosine of 0. And the answer to that, guys, is going to be, again, what angle? And let's see, inverse cosine is in the first and second quadrant from 0 to pi. What angle there has a cosine or an x value of 0? That is going to be pi over 2. So that's our answer then in radians, and in degrees, of course, that would be 45 degrees. And if you go back and kind of look at the two different variations I drew, as well as this one here as well, what we're now saying is that if that theta right there ends up being, I'm sorry, that pi over 2, my mistake, guys, is not 45 degrees. Let's try that again, Mr. Fontana. That is 90 degrees. That if this was a right triangle with your right, I didn't draw that well at all, but a right angle up here at the top, okay, pi over 2 radians or 90 degrees, that is the best possible way you could get this thing to work out. This triangle's area would be greater than this triangle, or even this one. That one doesn't really look like it was drawn with a right angle. So that 90-degree angle is the best possible way to do it to maximize the area of that triangle in number 15.